who have come are lucky. Those have not come are not that lucky.
तुम्हाला काय बोलायचं?
नाही नाही.
Okay. So introduction देऊ का?
नाही नाही. तुम्ही make that basic music.
Okay. So welcome everybody to the Radio Astronomy Master School. आज आपला पहिला दिवस आहे.
नाही नाही. इंग्लिश आणि हिंदी.
Okay. So this is our first day here, and the topic of today itself is the introduction to radio astronomy, and we are basically trying to investigate the angle in which radio astronomy is different from optical astronomy. Things so starting, we have some questions. Does anybody know what is astronomy? I'd like to answer for from you.
Astronomy is the study of stars, space, planets.
Any additions? Seniors?
Astronomy is like the study of everything in our entire universe. Like we can go from small scale, locally in the solar system to like going further away and everything.
Okay, so astronomy is also quantum physics.
It's not complicated. It can be applied in astronomy.
And astronomy can be also applied to biology. So yeah, basically astronomy is study of anything beyond the Earth.
इथे बंद करतो का?
Earth's atmosphere. And astronomy is any study of everything beyond Earth's atmosphere. So we study stars, we study gas clouds that exist in galaxies, supernova phenomena, and heavenly bodies. Anything that's beyond Earth's atmosphere. That's astronomy. Next, why do you think people started to study stars? We have seen a long way, many developments in astronomy happening. We have Copernicus, Galileo, and Indian astronomers, Aryabhatta, Madhava. All of these guys, why do you think they invested their time and efforts into studying and modeling astronomy as we know of today? Any ideas? Curiosity is a right answer. Anything else?
They try to do astrology, connect with astrology, predicting future events.
Predicting future events because the yes,
For navigating.
So for predicting future, as in keeping time, seeking patterns. Let's say monsoon starts in June and July. What was the position of the stars in June and July? And then I can predict the monsoon as per that. Then we have sailors and ship captains who used to look at stars and sky charts, and they used to navigate. But there's also an emotional kind of reason that we have been born from stars created by the universe, and we want to know what our origins were. How did Earth came to be? How did the universe came to be? How did the solar system came to be? So that's it. And the last question is, what tools do you know of that we use to observe space and study astronomy?
Satellites,
Satellites, telescopes,
radios,
let's begin with an activity. So I'll give you 2 minutes. You have to sketch a telescope. Anyway, imagine whatever you like, refractor, Newtonian, anything, space-based, ground-based. Just sketch a telescope in 2 minutes. You have a pen paper?
स्केच काढायचं.
sketch card, telescopes. Definitive particle. I don't ask you to sketch radio telescope alone. You can do anything you want. Optical, X-ray, gamma. There are many spectrums at which you can look at the sky. Another important thing I forgot to mention, does anyone is confident that they write or take down some really good lecture notes? Doesn't have to be good handwriting. Just noting down anything that goes in there. You can do that? Notes.
Points to that.
You have to put it up publicly. Future.
स्केचिंग केला तरी चांगलं होईल कारण स्केचिंग पुढं आर्ट ॲक्च्युली मॉडर्न टेक्नॉलॉजी स्केचिंग पुढं आर्ट.
So, come on up to the stage. No.
मला दाखवायचं.
So he wants to explain what his design is about.
दाखवलं सगळं.
Yeah, right. So this is his telescope. It's a
Exactly don't know what it is, but I have students started information.
okay. So this is an Newtonian telescope. Explain the components of it, how it works.
Reflected आहे.
This is the body of the telescope. Lens, I don't know. This is a lens and it reflects the image of this mirror and
Okay. And that is right. You put your eye up there and you look at the sky. Anyone else who has finished their work? Simplest refractor.
मला चांगला लागला.
This guy has come up with two telescopes. There's a tried to draw a parabolic radio telescope.
Reflected.
आँख कहाँ पे जाती है, स्टार कहाँ पे जाता है?
I do.
this is the artist, it's the main lens in the
Reflects. Where does it reflect? So this class of telescope is called as a refractor, right? sometimes a mirror. That guy has drawn the mirror. It's a diagonal. It's called as a diagonal. So instead of eyepiece, because you know the telescope is long and when we look point at the sky, sometimes ऐसे देखना पड़ेगा वेट करके, right? So there's a diagonal mirror, so comfortable position पे आ जाए. Okay, good. And so I like each one of you to answer. Speaking. Are these favorable conditions for your telescopes? This is a cloudy day, cloudy evening. Is it favorable? Okay.
I have a question.
Okay.
Like for telescopes, if we use cloudy conditions are bad because we won't be able to see through them. What about radio telescopes? Like, will they be able to see?
We will explain.
That's what the build-up is.
Slowly we are going to come.
Now the second one, it's a sunny day.
No.
Maybe you can use it for solar observations, eclipses, satellites. The third one is a cloudy night. Maybe some peaks at the moon, but visibility is pretty much affected. Fully grown city like Mumbai. Why?
Because the lights in the city, because of the lights, you won't be able to see stars.
Okay. And the third one is the countryside night.
अजून एक full moon व्हायला टाका. Full moon night.
Full moon, yeah. Full moon night affects deep sky observations of galaxies and Andromeda. If you ever go hunting for Andromeda or Milky Way, you'll see you most likely will do it on a new moon night because on the full moon the moon is pretty bright and
Whole night.
And the last one is space, outer space. So I think space we have the least kinds of disturbances, but also the most extreme kinds of and another level of disturbances. Hazards, and he knows what space, how challenging space is.
जायचं ना.
That's it. Okay. So out of these, I think the last two are the most favorable for an optical telescope. But for a radio telescope, you'll know that in all of these conditions we can do observations. The only thing limiting radio telescope is the ionosphere, as in disturbances outside the atmosphere where due to some phenomena charged ions can be produced and these ions reflect or absorb or scatter radio waves. I'll talk about that later, but yeah.
So cloudy also. Silver night cloudy.
Now why do you think in each of these images, what is the main factor that is preventing us from building huge optical telescopes on Earth and doing astronomy from ground space? Clouds, anything else? Fast.
Light.
Light.
It blocks the light.
It blocks the light, it scatters the light. Dust,
Water droplets.
water droplets, CO2, oxygen. All of these molecules, the molecules scatter the light and these things affect our observations. Now, drum rolls, the greatest discovery in physics of all times, light is a particle. Now obviously this was a joke because light can be a wave. Light has a duality, it has a dual nature. Whenever it propagates in the form of either a particle or a wave. We want to see the light from the stars, we want to see the light from galaxies, we want to know what's up there and where it is. And light can be a wave, it can be a particle, it depends on how you observe it, but when it propagates, it has a dual nature. And then we consider it both, sort of both, a wave particle. Now, light has many different shades of its own, colors of its own. and the colors depend on the wavelength of light, and then the wavelength of light is the wave, and if you can see, it goes from ascending or descending order in terms of wavelength and ascending order in terms of frequency. You'll see the optical spectrum of light as in near IR and near UV, and the visible colors that we see with the eyes are only a very small part of the electromagnetic spectrum. Now, does anyone wonder why do we only observe this small spectrum? Why don't we observe it? Maybe there is a star which emits light in X-rays. Maybe there is a phenomenon, a really high energy phenomenon which emits light in forms of X-rays. Maybe there is a phenomenon where very low amount of energy is liberated and it falls under the radio spectrum, or some weird phenomenon, some charged particle around some distant planet decides to enter its magnetic field and radio wave is emitted. These emissions are also astronomical emissions. We want to see them. We want to know what's happening up there. We want to know what's the phenomenon that's creating those, and we want to know if where such a phenomenon is. So there are gamma rays, X-rays. These are really high energy waves, really short wavelength. They act almost as if they are a particle, as in the wavelength is so small we cannot detect it, and detect it as in see with the eyes with the interferences. But anyway, X-rays and gamma rays basically the same thing. Gamma rays are high energy X-rays, and we have ultraviolet, visible, and infrared. These three are the spectrums we use for optical astronomy, as in mirrors, lenses made out of glass and plastic, quartz, not quartz crystals lenses. Then we have the radio astronomy spectrum. We have microwaves, we have radio waves.
So if we build a radio transmitter which emits radio waves, but that is of the frequency in the visible spectrum, right? Will it emit visible light?
A radio emitter in the visible spectrum.
Yeah.
As in
That much high frequency, right? If the frequency is the only difference, a regular transmitter should emit light waves. Does it? I don't know.
regular transmitters, how they work is they have you have an antenna,
Right.
and you have some kind of circuitry, we just call it a transmitter, and the transmitter sends electrical signals to the antenna,
Right.
which causes the electrons in the antenna to move up and down,
Right.
and this disturbance gets induced in the form of wave. Now the thing that limits us as of now is how fast can you electrically disturb this electron along a piece of wire. This is the thing that limits radio waves and microwaves from infrared, because you'll see in infrared the wavelength of light is really small, and an antenna needs to be at least wavelength by could be smaller, but it needs to be a significant fraction of the wavelength. As in, we see antennas of wavelength by 10 at least to transmit some power there. And infrared, visible, ultraviolet, the wavelengths are just so small we cannot build an antenna of that scale, or create a high frequency clock of such high frequencies, terahertz of frequencies. That is the reason why radio astronomy is different from optical, because in optical you have CCDs, something called as a CCD, charge coupled devices or imaging sensors, other kinds of technologies which detect the photon. So there's a lens here, there's an incoming beam of photons. The lens focuses it on a flat electrical device which is called as a sensor. So there are multiple sensors here, sensor. And whenever photon hits one of the sensor, it transfers all of its momentum energy into it, and this sensor basically creates an electrical impulse, signal output. But in radio astronomy, you don't look at photons. You look at waves, because photon, I'll get into it later. It's a really low energy thing. Sorry, it's a really only applicable in optical and above. In radio and microwave, we don't talk in terms of photons, because each millisecond of a hardly can emit a large number of photons. These cannot be detected in quantifiable manner. And also, second thing, we don't have detectors for photon in such big sizes that require detection of radio waves. So that's the thing that differentiates. Yeah, also, because just of the scale, the wavelength of this light, can you come up here? I have the radio here. I'll like to just illustrate what this is a radio, this is a powerful UV fiber, and this transmits in two bands, in the 2 meter band, which means the wavelength of light is is about this size, right? So this is the wavelength, and the second band it transmits, the ultra high frequency band. It's the wavelength is 70 centimeters, which is about this size of his head. So you can imagine his eye is not going to have electrons that resonate with this wave. So we need to build antennas for radio astronomy. Second thing is differentiate radio observatories from optical observatories. Does anyone see a similarity or correlation between these four observatories? Many different shapes and sizes. This is the levels for observatory.
Those four observatories, they are situated in a mountain area, and where there is no urbanization.
Okay, so they are in remote places and they are in mountainous areas. So why do you think they keep them in mountainous areas?
To avoid atmospheric layers.
Yeah, to avoid the atmosphere, because when you go 1000 meter, 2000 meter, 4000 meter above sea level, the amount of atmosphere you have it goes down, and also the atmosphere becomes much thinner. There is not heavy gases or heavy dust does not interfere with the radiance, and that's why optical telescopes are situated on the mountain. But with radio telescope, there's no such thing, because the atmosphere is basically transparent. 70 centimeter of wavelength. To even scatter this wave, you need metal particle, something which can have free flowing electrons in it, at least the size of wavelength by 10 or wavelength by 20. So you can imagine there's not going to be metal balls in the air floating around. And that is why radio telescopes, you see, there is no atmospheric opacity for in the radio spectrum up to 10 meters. What happens after 10 meters is a different thing. But up to 10 meters of wavelength, in 1 centimeter to 10 meters, you have a very open window where atmosphere is basically completely transparent. And this is why we focus on radio astronomy. Radio astronomy allows us to get this big band, and imagine how many phenomena or objects in the universe transmit at those frequencies, and we don't get to see them because we are observing at the wrong wavelength. It's not the wrong wavelength, but different wavelength. Now, you see most of the electromagnetic spectrum is completely blocked out by the atmosphere. So
So why is it like that? Why is the gap?
Why is the gap? Because of particle size. Okay. The atmosphere, the particles in the atmosphere are not big enough to diffract or scatter the light.
No, but then afterwards, later on, also the black
Yeah,
gap should continue.
this is because of something called as the ionosphere. The ionosphere is basically gases which get ionized by the sun's X-ray radiations, and I have something called as the sun emits X-rays. It gets in the upper layer of atmosphere. It ionizes the molecules there. These molecules are free flowing, but the distances are between those ions are large. So what happens is HF radio or beam radio waves that don't have high energy, as in the handy I have shown, this has each photon of this light. I know I told you we don't worry about photons, but let's just say the frequency is proportional to energy. Now at this is a very high frequency and ultra high frequency radio. Very high frequency is 2 meters, ultra high frequency is 70 centimeters. Now the HF band, which is the high frequency, which is 10 meters and below, 10 meters and above, these bands are high frequency, as in they are lower in frequency as compared to this. They are lower in energy, but these low energy radio emissions, they don't have enough energy to penetrate through the atmosphere. The atmosphere reflects it and bends it into total internal reflection or some sort of total reflection inside the ionosphere. Sometimes we see it all depends on how much radiation the sun is emitting. So ionosphere could be strong, ionosphere could be weak. Sometimes the waves just penetrate through, sometimes they roam around the earth, orbit 1 or 2 times and then come back to you in the receiver side. This is interesting, these are the interesting things. This is something called as Rayleigh scattering, where any light hits a particle, it gets scattered in all directions. And this is why most of the atmosphere is opaque to other frequencies and wavelengths. So till now we have learned optical telescopes, they observe at shorter wavelength, nanometer wavelength. They don't have antennas, as in affordable antennas at this wavelength. And so what we detect is the photonic nature, the particle nature of light. But in a radio telescope we have longer wavelength, we have antennas and such, so we detect the wave nature of light. And optical telescopes, they have mirrors and lenses, glass, quartz, something which you can see. It's the projector right now, it has a lens. Whereas in radio telescope we have antennas. Antennas are completely metal structures. They are wires of metal or sheets of metal or things like that, which can have free flowing electrons in it, so that the radio wave can disturb those electrons and we can get a electricity. Now, something really interesting is just because of the energy difference in between these two portions of wavelength, we see that stars and galaxies, the stuff which is thermally active, which is hot, it emits in the optical spectrum, infrared and optical, infrared and visible, sometimes ultraviolet. Whereas in a radio telescope, things get much colder, as in the thermal, as in you must have seen something. The blacksmith heats up a metal, the metal turns red hot. So it's a thermal emission. Whereas in a radio telescope, you don't see that. You see instead gases due to some phenomena of gases or jets or some weird electromagnetic stuff, cyclotron radiations, which I'll get to you. So my question is, why can stars be seen in the using your eyes, not nothing about radio, using your eyes?
because the light that they emit reaches close.
Okay.
Because also written visible
They also emit a visible rays. But why can they be seen? As in, what emissions are going on in there? In a star.
thermal reaction, no?
Thermal emissions.
Thermal reaction.
Nuclear.
You can throw it. So,
There are various things which emit in the optical spectrum. We have electron de-excitation. Electron goes to a higher energy level, and electron in an atom goes to a higher energy level and it falls back. That's called an electron de-excitation. Excitation, de-excitation. The energy difference between these two energy levels gets transferred, gets radiated in the form of electromagnetic waves in the optical spectrum. There are thermal emissions, as in black body radiation. We say stars are sort of a black body. They emit in the black body radiation almost in every frequency or the width you have thermal emissions happen. Then we have plasma processes where inside the Earth's, the sun's atmosphere, the outer layer of suns, there's plasma and ionized gases, and they go around and they emit light. These are the layers of the sun, of the star. There is the convective zone, radioactive zone, and the core. What happens is photon gets emitted from nuclear reaction that happens somewhere in this zone, and these because of just how dense the star is, this photon takes a lot of time to get up to the surface, and then at the photosphere it gets emitted out, thrown out into space, and then it returns after 8 minutes of travel time in the space. But in radio E equal to h mu, the thing that does anyone know what E equal to h mu? Energy equals to Planck's constant into frequency for a particle, for a photon. But in radio waves, you'll just see it yourself that we don't care about that much. So this is a question, calculation question, maths question for you want to try out at 434 megahertz, which is right now the frequency at which this guy is transmitting. I want you to calculate what the energy is, and after that, I want you to calculate how many photons it has. It emits per second. Photons emitted per second when the radio is running at 5 watts. 5 watts means 5 joules per second. Per second.
करा काय? इथे multiply करायचं ना ते.
424 into 10 power 6 is 1 megahertz. 10 power 6. So energy equals to h mu. So Planck's constant, I have given the value is 6.62. Don't go too much into 6.62.
Energy को indicate करना मालूम है.
Joules per second.
Joules per second.
Joules second. That's the unit of the Planck's constant. Joule second. Now take the frequency. Okay. Down here. Frequency unit is per second. Per second. Hertz is per second. So per second goes down, it becomes second. So energy second. Joule second. Any questions?
Again, energy.
Yeah.
How many photons?
How many photons? Per second. 1 second. That is the photon. And what's the energy of an individual? That's really interesting. We already get it. Three. Do we have an answer? That's the energy for us. Photon. 2.87 into the power 30. What? Per second. These are in photon. Is photon generated or is the energy? Joule. I don't think so. I think 25. Because this is minus.
Minus 25 joules.
Minus
25.
minus 21 or minus 25. That's 25. Yeah,
28.
2.4 कहते हैं वही 28 25 is correct. Minus 25. Now the answer for how many photons are emitted per second is 1.73 into 10 power 25 photons per second. Now, you'd imagine each photon carries so less insignificant value of energy that we don't really try to depict it as a particle. But the collective sum of these photons, they create disturbances in electrical fields and electrons, and then we can detect those. But individual photons we rarely detect in this spectrum. So, I'd like to hear from you, where do you think those radio signals come from? I think I already gave you the answer a few minutes back. Where do the radio signals in the space, from the space, or on Earth, phone, TV, radio, where do these radio signals come from?
Source of radio signal.
You जरा एक दो नेम ड्रॉप केले. Where do radio waves come from? Anything. What emits radio signal? Antenna.
Transmitter.
Transmitter.
इलेक्ट्रॉन्स और खाली होता है डिस्टर्बेंस
De-excitation radio होता, but it happens at a really small level. It's small energy gap. It's not a hyperfine transition.
So is it like that the ambient light from the star gets converted into radio spectrum, right? Or something like that?
Light from stars gets converted into radio spectrum
By
due to Doppler shift or
like the
Hubble
whole
shift.
gases you.
Now this actually exists, but it's not light from stars. It's light. So, do you know how the universe was formed? The Big Bang theory. Now what it tells is there was an event of creation which caused the universe to explode, and there's a line after which we don't really know what happens. There's something there, it's called as a fog. What the fog was is that the medium the universe was made of, the medium the universe was made of did not allow photons to escape out, to travel much. And after the fog ended, as in the universe cooled, the energy of the universe changes rapidly. That's the whole point of the event. After the fog, photons at the edge of the universe, they travel in all directions. And universe is always expanding. This is something called as the Hubble shift. Hubble shift. It is basically like Doppler shift, but it depends on how far away you are staying, because at that stage of the universe is starting to separate apart and it's been traveling that long. Anyway, so the Hubble shift, what happens is light from optical or UV, and then visible or UV, at really far out in the universe, the borderline universe, the light travels through space, expanding space. It gets shifted out due to the expansion of the universe. It gets shifted out. So maybe the wavelength or something like this, it gets shifted to something like this. This was blue, this was red, and now the red gets shifted out. It goes into infrared. The infrared gets shifted out into microwave, and that is what cosmic microwave background radiation is. Anything else? Radio signals? Any radio?
Does the universe expand faster than the speed of light?
Yeah. Cosmic microwave diagram. Thank you for connecting with the next slide itself. The cosmic, the photons released at the time of the birth of the universe gets stretched out into the Hubble redshift. So redshift, so redshifted that it is observable in the microwave spectrum. These emissions are like regular photonic emissions, but they get extremely redshifted to millions of light years. Okay. I already explained just that, and it looks something like this when you observe it with a radio telescope in the microwave radio spectrum. The discovery of cosmic microwave background was a really interesting thing in itself.
रेडशिफ्ट है ना, मतलब एक्सट्रीम डिस्टेंसेस साठी आहे ना.
हाँ,
It's not for the near object ना.
it's from the edge of the universe.
Right. But we are talking about radio astronomy in the context of near objects also.
Yes, we are talking about radio astronomy in all of its forms.
This is one of the forms.
This is one of the forms. So even the birth of the universe can be seen in the radio astronomy spectrum. Now, this is really interesting how they actually came to know about cosmic microwave background radiation. There was just 4 kelvins of antenna temperature mismatch predictions and observations, and this 4 point something Kelvin was then attributed. I may be wrong with the values 4 or point so really. That was the beginning. That was the detection of the cosmic microwave background. And later they created high resolution images, high resolution radio scans of the sky, and you can see everything. Sort of random, but it's also got some beauty to it. There's this thing is called as the signature. Now ignore these two lobes. What you see right here, the small horizontal in this axis, there's a galaxy. So the galaxy, you can imagine the galaxy is really small. The galaxy is something like this, and it has 2 jets of hydrogen gas, various kinds of material, stars, and jets are being thrown out in 2 directions. And you can observe, you can see those jets, those gas clouds that this galaxy is emitting is much larger than the galaxy itself. And what's causing this? there's a black hole in the middle of any spiral galaxy. The black hole is what causes the gravitation of everything, which causes all the objects to spin around it. In this supermassive black hole, when something gets close to it, it ejects it outwards into the axis. That's how this is called as the radio galaxy. This was the first radio galaxy found, and it was the first. It was found out by Grote-Reber. Grote-Reber was a ham. He was from Illinois, and Grote-Reber is such a legend. His ashes are kept at GMRT. His final wish was to be inscribed in all of the radio telescopes in the world. And that guy he was amateur, he was no professional or anything. He just wanted to know if the sky emits radio waves and just emits radio waves, and is there some shape or some kind of interesting things he can look at. And he created some of the first sky surveys. Now, coming to hyperfine transition, the electron d excitation we just talked about. This is a hydrogen atom. The hydrogen atom has a proton in the middle. There's a proton in the middle, and there's an electron spinning around it. The electron has a spin, plus half or minus half, it could be anything, related to the proton. The proton also has a spin, and the electron. So, what happens is when these both are parallel, this is a high energy state because this is spinning the same way, this is spinning the same way, both are trying to oppose each other. They are not complementing each other, both are trying to somewhat oppose each other. And this is a higher energy state. Now, when the universe was created, almost all of the hydrogen was in the higher energy state. As the universe cooled down, gases cooled down, millions of years, even hydrogen in your balloon may cool down at some point of time and it shifts. The phase of the spin of the electron shifts from a parallel spin to an anti-parallel. And this is what causes the 21 centimeter radio emission. The frequency of emission is 1420 megahertz, wavelength is 21 centimeters, and that is what the telescope is about, the telescope outside. It observes the hydrogen, neutral hydrogen. It's not ionized, it's not thermally active, it's just hydrogen that decides बस हो गया, अब ज़्यादा स्ट्रेस नहीं लेगा. And because the quantum number is only the spin quantum number is changing, plus half to minus half, and that is why this is called as hyperfine transition. It's not K shape to L shape to K shell, N1 shape, N2 shape to N1 shell, or it's not transitions between subshells of an orbital, or the orbital is changing. Orbital is not changing, only the spin is changing. And that very small energy gap between the spins, just the spin states, is what causes those emissions. Another kind of emissions that we see are something called as cyclotron emissions, where we have a really strong magnetic field, magnets. Now, what causes really strong magnetic fields in the universe? Anyone? Core of a planet or core of a star. Anything that has a concentration of mass and metals in it, and then it creates a magnetic field around it. So Jupiter has a magnetic field, a really strong magnetic field, in fact, the strongest in the solar system. And there's a really interesting moon of Jupiter. It's called as Io. Now Io is the surface of Io is full of volcanoes and eruptions happening. So it's throwing out matters into the orbit of Jupiter. It's throwing out mass. It's losing mass over time. Sometimes the mass is charged ionized particles, and and these ionized particles are stored in the blue ring around it. The ionized particle get thrown out, it moves through the strong magnetic field of Jupiter, and this creates radio waves because the charged particles get accelerated into a circular motion. You may have studied a simple charge. If I talk about a simple electron, a simple charge will create an electric field around it. It creates an electric field around it. When this charge moves and this electric field is disturbed, it's called it causes a magnetic field around it. And when the charge is accelerated,
electromagnetic field or magnetic?
if it's caused due to moving of charges, it's an electromagnetic field because there is also an electric field associated with it.
Magnetic field is different, right? Totally different.
It's the same thing.
It's the same thing.
It's the same thing. And when electron is moving, just moving, it causes a magnetic field. And if the electron is accelerated, then it causes a electromagnetic wave to form. The propagation happens. It propagates. Disturbances in electrical and magnetic field propagate. When electron or any charged particle, protons or electron, gets accelerated. That's what happens here. The ions get accelerated or deaccelerated, and in the presence of a strong magnetic field, they emit electromagnetic radiations. And you must be wondering what this white hole is. So there was a probe sent by NASA called as Juno, and the white line you see here, the large right line, it's the orbit of Juno, the flyby. So what they observed is when Juno went into this hole, as in you can imagine, just near the poles, but not exactly upon the axis, it's somewhat slanted from the axis, tangential to all those magnetic field lines. In this hole, we could have the Juno probe observed radio emissions in the Jovian spectrum. We have some time to
म्हणजे कसं
discuss.
त्याला इलेक्ट्रिक चार्ज when it moves it creates a magnetic field, and when it accelerates it releases the radiation.
Oh, actually,
So it's stable.
right. EM waves, we are going to come on EM waves and this is in space. So, should I start right now? Okay. EM waves, we have a wave. I just told you how EM waves are formed. But I would like to hear from you if you have some ideas on how you would go about making our own EM waves, electromagnetic waves, radio waves. You are tasked with generating anything.
If we take a battery and connect, if we take a cell and connect two wires like this and attach it to a coil like this, and we take another same but
डीसीला इंडक्टन्स लावून नाही ट्रान्सफॉर्मर नाही डीसीला म्हणून मग ट्रान्सफॉर्मर नाही बोलू नॉट ट्रान्सफॉर्मर अरे हाऊ टू क्रिएट रेडिओ एमिशन
How to create radio?
त्यांनी एक आयडिया सांगितली
कोणती तार क्रिएट करते हा तार कोणती कंडक्टर
त्याची कॉल
This
केली
is a DC source, right? Any coin battery or chemical cell it is a DC source of electricity. It's plus 9 volts, I think so. And
It's oscillate
some
magnetic
I
field.
current flows. And now due to Ohm's law, this I current and this is related to each other, and the current is same. current same way unless you vary something in this direction.
रेडी करायला
Now, what you have shown here is something called as a transformer. But the transformer will not work with the DC current.
त्यामुळे त्यात शब्द नको. It is not a transformer, it is an inductance. It is an inductance.
It is creating an electromagnetic field, and this electromagnetic field does nothing to the other side. The bulb will not glow
Yeah.
unless you put some switch here.
Now you can.
Okay.
And this switch is I have really fast fingers and I flick it on and off and on and off and on and off.
So, AC currents.
Changing current, AC or anything, changing current. When the current changes this electromagnetic field, the varying magnetic field generates an electric current in this coil solenoid, and this will then light up the bulb. Now
Then you
this,
can call it a transformer.
then it's a transformer. It's still not propagating EM wave because I take this thing out and I put it here where the magnetic field lines are not that strong. It's not going to
Travel.
travel.
So, it's a field, not a wave.
It's a field.
It's a field.
That's correct. It's a field. It's not a self-propagating wave.
Wave.
It's not a wave. But okay, well tried. Anyone else? There are many ways you can
देखो वेव सांगा था. Enjoy करने.
Yes.
How you can create a wave?
There are many ways of creating a EM wave. All of them involve accelerating a charge.
I have known that you can make a manual pattern that would point out the
Okay. So basically, what I just said, I just put a switch there instead of a point.
But still it is a field, right?
But it's a field. A solenoid creates a field. It's not an antenna.
Not a wave.
For propagation to happen, you want the fields, the disturbances to leave the solenoid. So travel करने चाहिए through empty space. Yes, one property of EM waves is that EM waves can travel without a medium. There is no need for electrons or gases to be in there. It's a self-sustaining cycle. I would get into say equation, but I don't think you will understand divergence and
I think even solenoids should generate electromagnetic wave, right? If it's changing
it
current.
creates electromagnetic fields, but it does not create propagating electromagnetic
Because my understanding is that if changing current is passed through any conductor, in piece of wire, it will generate electromagnetic wave. That's the antenna. Even waves. Yeah, it does.
It needs to be traveling. Now this
Hardly it will
yeah,
travel.
wants to talk.
Are EM waves only sinusoidal waves or also have different angles, square waves?
Electromagnetic waves can be any wave. Anything.
Where must stay?
Where now there is some. I'll get into it later. Okay. All of them involve accelerating a electron.
Acceleration वाला.
Acceleration of a charge.
That. Then it is called wave.
Let's say I have a metallic rod and I am using some kind of electromagnet, solenoid or directly connecting a wire to it, some kind of force to push a charged particle, whether it's a positive or a negative electron, a charged particle up and down this metallic rod, and the metallic rod is resonant. So let's say I have two metallic rods. This one has a positive current. As of now, just I have connected it. मतलब अभी कनेक्ट किया है, अभी उसको वायर लगाया है. This potential difference causes all of the positive charges to rush up there. वो rush करें. they are fleeing away from the potential difference, the electric field. So the acceleration that happens here, and at the end, when the charge particle reaches the end of this thing, I'll switch it to off. Correct? Or reverse it. And now this goes accelerated down.
Yeah, you will start oscillating.
And now I'll create some kind of circuitry that does this for me. So I'm accelerating, deaccelerating, and it always hits this wall. This what we have created is a monopole. Let's forget the down part of it. It's a monopole. So it's creating a wave. It's
The way it is creating this type of wave, when it goes there, does it create a logarithm
on the axis. So radiation pattern of a dipole, something like this. This is the dipole, basically monopole with two antennas. It's two poles, no metallic ones. So one for positive, one for negative, balance. So this has a radiation pattern, something like a donut shape. It only transmits energy along this direction. It does not transmit exactly on the axis. And I hope that answers your question. This thing does not travel on the axis. How do you block it? Very, very interesting question. Now, just what I said, like a metallic rod. I have another metallic rod. Now, when a wave hits this metallic rod in metal waves, sea of electron or sea of charge particle, everyone is free to move anywhere. Charge carriers react to this electrical field of wave. The wave has electrical and magnetic field. It reacts to the electromagnetic field and it creates a current. And this current opposes this wave, and basically ahead of this conductor you won't see the wave going on because it destroys the wave right now because of the current. So yeah, if you want to block a wave, you want it to create opposing current. You want it to react. So this is why the ionosphere was not penetrable by HF radio wave, because the ions could move at those frequencies, and the moving ions could cause the EM wave to be reflected back.
So jammers are a much powerful version of that rod.
Jammers are completely different too. Jammers are transmitters. This is left side transmitter. This is a transmitter, and it transmits high power radio waves, so that weak transmitters like your mobile phone or radios, they cannot listen. They cannot be selective, sensitive to receive or transmit anything.
They are not absorbed.
I think they're
If you place a wire mesh, it will act as a Faraday cage.
yes. Wire
You
mesh.
don't need a current, right?
You need electrical continuity. You need the wire mesh to happen. If I just have really small metallic tubes and I put them in such a way that there's no electrical current that can flow or electrical fields that can occur between these two. So let's say I put them like this. What happens is there's the electron, the charge carrier don't have much distance to travel. Right? So it does not, reflect the wave or.
But we don't need to supply external current, right? it is the current that is generated by the wave in the mesh.
Huh.
Right.
Yeah.
We don't need to supply
You
external
don't
current.
need to supply.
But we have to sync it.
Yes, something like
We have to sync it somewhere.
Okay. Yeah, ground making it, make it
Something like
ground.
that. No, no.
But if the mesh
the
is
path
large
to the
enough,
current.
then if the mesh is large enough, then maybe you don't need a
But still where the current will go?
whether it's a AD or something. Yeah, or because the object is large.
Yeah.
Perhaps.
anyway, now coming to the next point is how do you define any wave in form of an equation? Already the सामने रख दिए. So yeah, this is the equation for a propagating sinusoidal wave. Waves can be of many types. There are many shapes to a wave. There are many frequencies to a wave. If I just show you the next slide. This is a wave, and we are looking at it as per time. But if let's just ignore time and put distance there, distance or displacement, and whatever this called, whatever distance one cycle of the wave covers, it's called as the wavelength. And in time, whatever distance, whatever time the wave is taking to complete one cycle is called the time period. So, frequency of a wave is 1 over time period. And then how many times in a second does the wave oscillate? If a wave has a time period of 1 millisecond, it oscillates 1000 times in a second. Now there is something interesting. This is a circle. This is completely imaginary. Imaginary. This is the imaginary plane. Let's assume we are making a right angle and we have angle theta between the opposite and the adjacent side, and we take the sine value of it and plot it on the graph. And now I keep increasing theta slowly by slowly. Now you see the opposite side is growing, and at one point it hits the top of the circle, and at that point it starts descending down. After the positive, after the top two quadrants, the opposite from the side goes into the negative, and that is why you see. Okay. This is imaginary. The x and y, maybe this. The opposite side is the only real part of it. We are plotting on the graph. Now, there is something interesting with the sine function and cosine function. Now, do you know what the relation between a sine function and cosine function? It's really simple.
Complementary.
Complementary. They are complementary to each other. As in, sine of theta is equal to cos of 90 degree minus theta. Or in terms of radian, we call it as pi by 2 minus theta. This is in radians. So, if you can imagine, when the sinusoid is at, when the sinusoidal wave is at 0, the cosine of the wave, as in the adjacent side, is at 1. So when this is at 0, the cosine will start from 1 and it will follow just the same direction, but with the pi by 2 phase shift, as in it's leading it by pi by 2. It's happening before the sinusoidal wave reaches 1. And you could take this sine out and put the cos there, and just change the phi and it will be basically the same wave. So sine and cosine are the same thing. And what you see here, the W expresses the angular frequency. It is how many cycles does it cover. So angular frequency is very much related to our normal cycler frequency is 2 pi times the frequency is equal to the angle, right? this thing, the angular wave number, this determines the wavelength. Right now we are not going to do much maths with it, but there's something I'd like to introduce you to the frequency and wavelength relation. So what happens is okay. So what happens is we have a wave that's going, right? It's traveling with some certain propagation speed, which we'll call as or c, and it has a wavelength, as in how the distance between one cycle, the distance it takes to complete 1 second. This is called as the lambda. This is the distance, and there is a frequency. Right? Now, the frequency affects how many cycles can be done. Now, frequency, wavelength, and the c. These are related using a very simple expression. The speed is equal to wavelength into frequency. So, yeah. So, rewrite again. So, this is a wave, this is cycle, this is lambda, and c. Now, what you'll notice if we keep the same speed and we increase the frequency, now the wave is going to oscillate much faster, right? So, it's the same speed, but we are oscillating much faster. What that causes is the distance between when one cycle starts and ends, the lambda goes down with an increase in frequency, and it does that proportionally. So that's what the relation is about, and you can find out wavelength of a light given its frequency and speed of, and speed of light in free space always remains constant in free space. Only thing that can change the speed of light, as in the speed of light does not change because light is not traveling through a medium. What happens when some molecules of the air are incident with the EM wave is that these molecules, as I said, they oscillate somewhat and they create their own wave which overlaps this wave, and it tends to create a slower waveform. This is the waveform that goes slow, the phase is kicked back.
Resultant.
Delay होता है बस.
Resultant है.
हाँ, resultant is delayed, but the actual wave is passing through. The actual wave passes at the speed of light. Because wave does not need a medium travel. It will not stop for anybody. But some people will try to but it will not stop. But it will just appear as if it has slowed down. So that was a. And again, coming back to there's, as I said, a medium or any obstruction in the way of light, can either reflect the ray of light by oscillating at a particular at that wavelength and oscillating it such that the entire wave is reflected back and the back portion of it gets cancelled out into interference. I am not saying that the ray of light does not go there. It does, but if depending on the characteristic of the particle which is being struck with light, it will determine at what direction or which determines refraction. Again, transmission and refraction. It determines what is the characteristic of this particle.
That's the Tyndall effect.
Tyndall effect. And some particles, they are like damping springs. They are like dampened springs. If I try to oscillate them, they will take my energy and they will not. They will move, but they will come back to their original place and they will dampen the oscillation. These guys cause absorption of light. And some particles, they will take all the energy in at once and they will scatter it out all at once in all directions. This is called scattering. The antenna, this is a dipole. You can imagine how the charges flow and how the EM wave is generated through a dipole. So you can see the charges are this device here is causing the charges to move back and forwards and it's creating a EM wave. Or you can use the inverse of it. Of that, an EM wave is coming and hitting the dipole and it causes the current to move along and you can receive it to the receiver measure it. Now there's various type of antenna. As I told, the particles, depending on their size and nature, they can either transmit light, they can either reflect light, or they can scatter light. These things can be made man-made using wires and metallic structures. So we have a Yagi antenna. It has a reflector back in the back. The reflector is larger than the lambda by 2.
You remember these antennas?
Yes, this one.
So you for the TV television, the past 30 years back.
Whenever an object becomes larger than lambda by 2, it reflects light. So this thing is going to reflect whatever emission. This guy is going to transmit. This guy is going to reflect it to the forward direction. Or you can take it in the inverse way. The forward light comes in, hits the reflector and gets concentrated in this area. There are some parasitic elements, we call them, directors above the antenna. These directors are going to transmit the light and focus it, act as a sort of a lens to narrow the beam of light. This is a helical antenna. Now, we were talking about one axis, one linear. Now just think of two axes, and now we are having a 2D wave, which is called a circular polarization. The wave has electrical and magnetic components that alternate between each other. So as you know, a wave has an electrical field and it has a magnetic field which is perpendicular. Now what happens if I just rotate this wave in the 3D direction? This is what you end up with. Because the electric field was initially traveling in this direction, now it's traveling in this direction. The electrical field, now it's traveling in this direction and so on. It is rotating. This is a parabolic dish reflector which we use. The dish or the reflector is going to reflect the light, reflect the radio waves, and it's going to be concentrated in a field. The field has either a dipole or a monopole or there are many weird kinds of antennas. People have come up with many different shapes of antennas. So that's what transmitter and receiver looks like. You will see this thing is called a mixer. This mixes two frequencies together. This is a local oscillator. Local oscillator is like a clock. It's generating those frequencies. It's the thing that keeps track. It is determining the frequency at which I am turning the switch on and off, on and off. That is, the switch is mixer and the local oscillator is the turning it on and off machine. And you will see I have an antenna here. If I turn if I send, let's just keep it a DC source, positive. Okay. There is a switch and the switch is controlled by this local oscillator. The local oscillator turns the switch really fast on and off, and this generates a changing current and changing waveform. Okay? It generates an electrical signal of frequency determined by this LO. Right now we are taking 0 Hz here, DC. Okay? So the local oscillator is going to determine the frequency. And then the signal goes on through amplifications. We have amplifiers for that. It gets amplified and it goes into the antenna. That's how things are radiated, and the same thing in reverse is the receiver. Now with the receiver you don't have DC here. What happens is the mixer, this will be taught in a later lecture, but the mixer will always give out two signals: the frequency of the radio wave that which was being received from antenna and frequency of the oscillator. And the other thing it gives out is frequency of radio plus frequency of oscillator. It gives these two outputs. So you can imagine if the frequency of incoming radio waves is 10 megahertz and the LO is at 12 megahertz, the output signal will either be 2 megahertz or it will be 12 megahertz. So for that we have a filter. So let's say I have a detector which only detects 2 megahertz, so I'll place the filter there and I'll only take the 2 megahertz signal. And the 2 megahertz signal I can detect it and listen to it. Now we have audible frequencies, right? 0 to 20 hertz, you can hear it with your 20 hertz, 20 kilohertz, you can listen to it with your ears. Now what if we just have the local oscillator to adjust its frequency such that the source we are listening to, the frequency gets down converted. Let's say it was 10 megahertz. Now the frequency of oscillator will keep it such 9.9 megahertz, and the output will be 0.01 megahertz, which is equal to 10 kilohertz. 10 kilohertz. Now this waveform, this output, you can listen to it with our ears. So what I do is I put an audio amplifier out here and a speaker, and now I can listen to radio. That's how basic radio receiver works, and the filter just needs to be that. That's one part of it, which I'll get into later, which is called as image rejection. The mixer, it's a switch, sort of a switch. Turns one signal on and off with respect to the other signal, which causes these two signals to mix and form a waveform. Now I will stop here. That's the end of the EM waves side of the lecture. शिरीष जी आली.
चालू आहे चालू.
आताच ब्रेक लागला.
हो का?
हां.
मी दिल्लीला होतो.
हां.